Is Pete Whittington. My name is Pete Whittington. I'm the president of the hydrology section of the Canadian Geophysical Union. Barrett might be popping in and out during this session as co-convener, but I believe he is convening the third session this afternoon. Our first speaker is Peter Lawford, talking about the evaluation of soil erosion models for application of the Canadian prairie environment. Take it away, Peter.
Okay, thank you, Pete. Just to introduce myself, I'm Peter Lawford, and I'm working with John Pomeroy as a PhD student. And I want to talk today a little bit about soil erosion. So if we consider soil erosion, there are several issues that arise from or are exacerbated by, and specifically water-driven sediment erosion, which is what I'm most interested in the Canadian prairies. And we can divide these into on-site issues, such as deterioration of the agricultural arability, and off-site issues, particularly eutrophication and deterioration of aquatic ecosystems. And eutrophication is particularly what I'm interested in the end, but the relationship of sediment erosion to that. So let's consider what the issue is. Soil particles are detached from the soil matrix by water rain splash and by flow over the soil, and they absorb phosphorus as well. And those soil particles are transferred via streams into our aquatic ecosystems and cause damage in that way. Several types of damage, as I mentioned, eutrophication and other deterioration issues. So in order to understand this, we need to consider, first of all, data collection of water quality data is difficult, and we can't really collect data for the future. We don't know what future is. So we really need modeling to help us. But this requires accurate process representation. And so I mentioned here just a few of the processes that need to be considered for the prairie specifically, and are not always considered in models that are applied from other areas. In fact, never considered really. Particularly the winter processes, frozen soil erodibility is a big one. And for summer and year-round processes, there's variation within the basin of connectivity and a contributing area, which need to be considered. So I have a site in mind that I'm interested in, and of course I really would like to have more data. My site is South Tobacco Creek, as you see marked there in Manitoba. It's in an area that has a relatively high soil erosion risk index compared to some of the other areas. So I think it's a good area to be researching. And it's a watershed evaluation basin by AAFC of beneficial management practices. It's a study site for that. And I've been given some water quality data by Jane Elliott of UCCC, and I'm thankful for that. Of course, I'd like water quality data from other areas too, if it's relevant and helpful. But this is a good representative of prairie's water-based sediment erosion issues here at South Tobacco Creek, I believe. Here's just an outline of what this South Tobacco Creek looks like. It's 74 square kilometers. It has a fairly high, for the prairies, difference in elevation between highest and lowest, because it has an escarpment, and it's mostly cropland, 78% cropland. So I've marked here the outlet and the midpoint. I'll be talking mainly here about the outlet. When we do analysis, there are several contributing factors to water-driven erosion: climate, the soil properties, land cover, land management, and topography. That we need to know the information about our basin for each of these. But I'm going to focus mainly on directly hydrologically relevant driving factors. And we can also consider the water-driven erosion subtypes, interrill, rill, gully erosion, and then there's one more, channel erosion. But because this area, 74 square kilometers, is somewhat small, it has streams that are temporary. That is, that they don't flow all year round. And that is going to be another issue for considering sediment erosion in this particular region. Now I'm going to get back onto the model families here and how we model sediment erosion. Probably the most famous one is the universal soil loss equation, which has been developed by the Department of Agriculture in the United States. And there are some, I guess you could call them child models of this original model, revised USL and modified USL. And this is used in the SWOT hydrological model in order to get sediment information. And the SWOT model has been run for South Tobacco Creek by Liu and others in 2014. Now, if we look at the fundamental equation of USL, we can see that there's an issue that the concentration isn't expected to change very much. It's considered nearly chemostatic. And so this is going to be a question whether this is a reasonable assumption or not. An alternative model that I think is maybe more interesting is based on this Morgan-Finney, and it comes up in HYPE and in a more recent model, CRIM-WQ, which is maybe the model that I'm most interested in. And this model considers rainfall detachment and streamflow detachment separately, whereas the USL model just had just an empirical formulation. In particularly the HYPE model has also a storage release component to calculate concentration in the stream. So now let's consider whether that original chemostatic assumption was valid or not for South Tobacco Creek in these temporary streams. Here I'm just showing you the relationship between stream flow and sediment concentration at the outlet, Miami. And you can see that it doesn't really look chemostatic. It looks like higher stream flow will give you higher sediment concentration, both in the summer and in the spring. But it's also important to recognize that these two periods, these two seasons, seem to have different behaviors. And I guess you would expect, if you know the physics, you would expect that they would have different behaviors, and they do. Of course, it's also important to recognize that high stream flows and low stream flows are both important to be simulated, because half of the cumulative stream flow outflow from the outlet at Miami is contributed by flows that are less than 2.2 cubic meters per second. So low flows are important in terms of calculating the total sediment concentration. If we look into the spring season particularly, we can see that the sediment concentration in the first portion of the spring is fairly low, and then in the second portion, it rises up. And this is not really too surprising either, because sediment is not really eroded well when the soils are frozen. And as the soils thaw, then more erosion can occur. And this is also something that is not well captured by current models. So if we look at the data, here's some data from South Tobacco Creek for a particular event. Now this is a spring event, and we can see more clearly that there's a thaw procession. And then as the soil thaws, the amount of erosion that is occurring, the concentration of sediment in the stream increases. And if we look at summer as well, we can see a different paradigm here. We can see the detachment by precipitation, and then there is a recession limb. Basically, the concentration is originally high because of the detachment from the soil, and then it slowly drops down. And this is somewhat captured by the storage release mechanism in the HYPE and the CRIM-WQ models. But I should mention here that the recession limit is not the same for every event. So if the model has a single value for the storage release storage quantity, it will not capture well the changes in concentration. Now the focus of my research is this CRIM-WQ water quality model. that has been developed based on the original CRIM model by John Pomeroy, and it's been extended by Diogo Costa. And the actual the specific configuration for South Tobacco Creek was done by Tawfiq Mahmoud in 2017. And so this model has some good modeling of snow and cold regions processes, but not those related to sediment erosion specifically. So my work is to improve that erosion modeling within CRIM-WQ. And I'll just show you some results of this. This is before the improvements to sediment erosion, which haven't been completed yet. But we can see that the current CRIM model, CRIM-WQ model, does not well capture the spring melt events. So the soil changes in soil erodibility due to the thawing of the soil are not well captured by CRIM-WQ currently. And for the summer storm events, we're doing a little bit better, but we don't always capture the recession curve well for the summer events either. And of course, driving sediment concentration is stream flow. So having good stream flow results is necessary for having good sediment erosion results. So I'll just summarize here. The USO models and also the current MMF models have difficulty representing water-driven erosion in the Canadian prairies. Although the MMF models, like HYPE and CRIM-WQ, they have stronger conceptual and physical basis than the original USO model. And I think they have more promise for modeling. And CRIM-WQ in particular shows promise modeling cold regions processes, but it still needs improvement. And my focus going forward is to continue to investigate the potential improvements in modeling snowmelt and rain splash driven erosion, and to incorporate those improvements for spring melt and recession curve handling of the water-driven sediment erosion in CRIM-WQ, and to then apply this model across the Canadian prairies for future climate and agricultural management scenarios using a virtual basin methodology, which is used by several other researchers, quite a few other researchers in our group, Center for Hydrology. So with that, I would like to close unless there are questions.
Excellent, Peter. Thank you for that. I think we'll have time for a quick question, if anybody has one for Peter.
If not, then I'll just move on for the next presenter.
Okay. See if anything comes in the chat. If you do come up with a question, you can place it in the chat, and hopefully Peter will stick around and can reply in the chat. So is that Tobacco Creek? Is that David Lobb's site as well? He works out of there, I think. Is that right?
Yes, I believe so.
Yeah.
Yes, there have been several researchers that have worked on Tobacco Creek for various reasons, mainly for BMP evaluation.
Yeah, I think I've got a colleague just down the hall from me at Brandon University, Alex Coiter, that has done some work there, maybe during his master's or something. I can't remember. But, okay, we'll get our next speaker set up, Raj Tantra, and we'll get that started in about 30 seconds. So again, at about the 12 or 13 minute mark, if I can't tell that you're winding down, then I'll turn my video on, and then a minute or two later, I'll start interrupting. If people have questions during the talk, feel free to post them in the chat, and then I can either ask them or the speaker can follow up afterwards if we don't have any time. So our next speaker is talking about the impacts of climate change and anthropogenic activities on the hydrology of the Nachako River Basin. So take it away.
Yeah, thank you. Thanks. So, hello everyone. My name is Raj Santralilare, and I am a postdoctoral fellow at the University of Northern British Columbia. So, I'll be talking about impacts of climate change and anthropogenic activities on the hydrology of the Nachako River Basin. But first of all, I would like to acknowledge our traditional and unceded territory of Great Nethane, Prince George. And you will see the beautiful picture in the background. It's the Nachako River, and here is the city in Prince George. So, first of all, the impacts of climate change versus flow regulation to its hydrological responses and water balance are not thoroughly analyzed till now. So, particularly over the Nachako River Basin. And it is important to know the hydrological status of a river basin due to land cover disturbances, and hydrological modeling plays an important role to visualize and understand these effects on the watershed hydrological system. So therefore, our research objective is to quantify the impacts of flow regulation versus climate change on the overall hydrology of the Nachako River Basin. And the second objective is to quantify the impacts of land cover disturbances, for example, forest fire, deforestation, pest infestations, etc., on the hydrology of the Nachako River Basin. So moving forward, our study area, as you know, the Nachako River Basin, which spans an area of 47,200 square kilometer in the north central BC. And extending from the coast mountains in the west up to Prince George here in the east, where it meets to the Fraser River Basin and Fraser River, and contribute to the Fraser River Basin. So this is the second largest sub-basin of the Fraser River Basin and dominated by forests. So the annual air temperature in the Nachako River Basin averages from 3.7 degrees centigrade, while mean annual precipitation totals from around 600 mm, with about a third in the form of snow. So here you can see the schematic diagram of the Nachako River Basin. So there are the area here, it's heavily regulated, which is, we call it Nachako Reservoir, and the water from this area goes to operates and regulated by Rio Tinto for the hydropower generation, and goes through here Kameno powerhouse, and the tunnel goes here in the eastern side to generate the hydropower. And it is also regulated in the Canadian here and Skins Lake spillway, so that can regulate the stream flow, which contributes to eventually to the Prince George area. So this is the overall methodology of this work. So I'm using variable infiltration capacity model, which is the version 5 or the latest version of the model, and the domain is the Nachako River Basin. And we are covering the entire study period is from 1950 to 2019, and we are using ERF5 land data. And so for the first objective, we will be running the hydrological model and generating the hydrographs and comparing those with the regulated flows to identify the impacts of flow regulation versus climate change. To obtain the second objective, I'm doing a kind of a sensitivity analysis. So in that, we'll replace all type of forest with grasslands and see the impacts of land cover changes on the hydrology of the Nachako River Basin. So first step was to intercompare the input forcing data sets for the hydrological model. So across the 6 sites in the Nachako, we compared the precipitation data, and you can see here the ERF5 land data, which is represented in red color here, and the black one is the observed data from ECCC. So represents really well for the overall meteorological conditions. Same for the temperature data, you can see overlaps quite well, but for these 2 stations, which is in the hilly area, of course, is not doing good, the ERF5 land data, but overall, we see the satisfactory performance of the ERF5 land data across the watershed. So for the Big 5, so the second step was to calibrate and validate the model. So for the calibration, we selected 6 natural or unregulated tributaries in the Nachako River Basin. So these all are representing the triangles here. And this one, the Nachako Reservoir, so we got the naturalized flow or unregulated flow here at the Nachako River below Big Bend Creek so that we can calibrate this entire area. So these are the list of all 6 stations and the locations. So some of the calibration results. So you can see I'm presenting 2 of the best calibrated results in the Nachako River Basin. So the first one is the Nachako River below Big Bend Creek, the entire the regulated portion, which is calibrated against the naturalized river flow. So pretty good calibration validation result, getting more than 0.88 Nash coefficients in both calibration validation period and the KG coefficient more than 0.80 for both the subbasins. So the Stewart River and same for the other watersheds as well. So now moving forward, the flow regulation versus climate change impact. So here you can see the Nachako in the red color, Nachako River below Big Bend Creek generated from the Big Five model, and the black one is the Skins Lake spillway. So basically, that underutilized regulates flow and get the regulated flow to the lower part of the Nachako River basins from the Skins Lake spillway. So here you can see the naturalized flow in the red and the regulated in the black one. So we saw 42% of average reduction in flows. That means that is reduced due to regulations in the lower Nachako. In the second one, we saw the observed versus simulated hydrographs for the upper Nachako River. So you can see the red one is the Big Bend Creek is the daily flows, daily hydrograph water years, and the observed one at Big Bend Creek. So pretty well for the big model. And the blue line shows the observed at Skins Lake spillway. So here, this is the observed flow which is released from the Skins Lake spillway to the lower Nachako. So here you see in between 10th July to August 20. So this is a summer temperature management project where this project operates from July 10 to August 20 with the goal of managing water temperature in the Nachako River at Fillmore between July 20 and August 20, so that they can protect the fish habitats and basically try to conserve or try to manage the water temperature, because if the water temperature rises below a certain point, then it will be bad for the fish habitats. So that's why they just plan to manage those water temperature below 20 degrees centigrade. So that's the important part of this regulation as well. The second objective was to identify the land cover change and see the impacts of those changes on the hydrology. So for that, we had base run. So that is basically no change in the land cover data, and the sensitivity run basically changing the land cover data, substitution of all the forested area with grasslands, and see what is the impacts of changing those land cover in the hydrology. So here you see the land cover data I used for the simulation, so which is the AVHRR data. So this is the composites of images from 1988 to 1991 and produced one land cover data for the area. So here's the results for when we do the sensitivity run. So this is the difference of sensitivity run minus base run here. So in the percentage change, so you can see here in evaporation, we get mostly increased evaporation across the basin because there is no no forest, so only grassland. So that's why the water will be evaporate more from the basin. And then the second thing is surface runoff. So here we see the increased surface runoff. Basically, if you don't have any forest, then there will be increase in surface runoff. And the brown color here you see almost no change. So that means these are all the water bodies here. That's why we don't see any much change in that. And the base flow, of course, the more infiltration, less infiltration. That's why we are seeing the negative values across the watershed. So basically negative change in the base flow. This is the hydrograph of the Nachako River. So the red color shows the sensitivity run and the black color shows the base run. So you can see that when we replace all the forests with the grassland, so we see increased in flows, especially in the summertime. But the winter time, it's like similar flows, but in the summertime, we see increased around 2 mm per day increased runoff. So in summary, I would say that we found 42% average reduction in flows. I showed in the previous slides as from 1955 to 2019 due to interbasin regulation of flows in the upper Nachako River. Net evaporation increases less than 10% in most of the watershed when WIC 5 flows with grassland over forested area. And the surface runoff increases greater than 5% across the watershed, whereas relatively slight decrease in base flow. There is 1 to 1.5 mm increase in summer flows. However, no change in autumn and winter flows we found. So the next step would be to identify other water balance components and interlink those water balance components to see what is the overall impact of land cover change on the hydrology of the Nachako River Basin. So at the end, I would like to acknowledge ANSWER for their funding and support, and Rio Tinto, of course, for the data they shared with us and the funding support as well. And I would also acknowledge all the our energy group, which I'm working on right now. So thank you so much, and I look forward for the questions. Thank you.
Excellent. That was perfectly on time. I see a comment in the chat from Jason Leach. It says, it looks like you're using grasslands as a proxy for forest disturbance. Could you comment on how the grasslands class is and is not a good proxy for forest disturbance like harvesting and wildfire? So if you didn't catch all of that, it's in the chat and you can read it yourself. We've got 2.5 minutes for the response. Thanks, Jason.
Yeah, thanks for the question. So the idea behind the sensitivity run was just to see the initial, what is the response of the hydrological model first. Then we will play around and see the different land cover change. So for example, barren land. So the first thing was just to replace all the forests with grassland, but in the next step, we would also change our proxy with those with barren lands and combination of grasslands and barren lands and other classes as well. So the idea behind this analysis was to see if forest fire happens and we don't see any forest at all over the area or some impervious layer due to forest fire. So what will be the impact of those in that? So I think the good analysis would be with the barren lands as well, with impervious layer. So yeah, that's the next step for this work.
Excellent, thank you. We've got about a minute, so if someone else has a question, if not, we'll get Danielle to get ready so we can stay on time. Don't see any other questions in the chat or no hands raised. So Danielle, if you can maybe start sharing your screen and we'll get started in just a little bit. All right. Okay, so our next speaker is Danielle Hudson, talking about thermal regimes of groundwater and lake-fed streams differ in the response to climate change.
Okay, thanks. So yeah, my name's, am I good to go? Sorry.
Yep, take it away, thank you.
Yeah, so my name's Danielle. I'm a physical hydrologist for the Canadian Forest Service, And yeah, I'm talking about thermal regimes of groundwater and lake-fed streams. And we're going to be looking at that from a place of spot measurements and within a stream lake network. So just to frame this work a little bit, I mean, we heard a bit about it in the last presentation, but why do we care about stream temperature? We know that forested streams provide habitat for a wide variety of aquatic organisms, and it's a very important parameter for determining that habitat suitability. It also plays a role in ecosystem productivity and a range of processes, but there are concerns about how these temperatures are going to respond to climate change, especially for cold temperature species where we could see a restriction of their habitat potentially. However, efforts to identify exactly how stream temperatures will respond to climate change are generally limited by a lack of long-term stream temperature data sets. And this understanding is necessary if we want to manage our forests sustainably going forward. And then also, why do we need to consider stream-lake interactions? So streams and lakes are often considered separate components of the forest water network, but in reality, the two are strongly linked, and especially in regions like the Boreal Shield, where we see a high number of shallow lakes that are often connected by streams. And previous work has shown that there are interactions between lakes and streams, so lakes affect streams and vice versa, and these interactions do influence downstream flow and water temperature. So given the key differences that we know exist between lakes and streams, we might imagine that they would respond, or streams would respond differently if they are draining lakes or if they are groundwater fed. Yeah, so basically, if you have a downstream ecosystem, it's going to be affected by the streams and lakes that you have upstream and how those interact with the forest cover. So our research objective or question for today is, are these thermal regimes of groundwater and lake-fed streams responding differently to climate change? And to answer that question, we're going to be using spot temperature data from the Turkey Lakes watershed. This is a long-term experimental catchment study. It's located just north of Sault Ste. Marie, Ontario, on the eastern shore of Lake Superior, and it's located on the traditional territory of the Batchewana First Nation. This long-term study began in 1980. It's continued on to present day, so it gives a really unique opportunity to consider long-term trends in forest water dynamics in this Boreal Shield lake stream network. And it's 10.4 kilometers squared. It's got mixed hardwood coniferous forests, and there's actually 21 hydrometric stations here. 12 of them we're looking at today, 7 of which are lake-fed and 5 are groundwater-fed. And the study period we're focusing on is from 1983 to 2018, because that has data for all of the sites that we're interested in. So what do I mean by this spot temperature data set? So we are going to look at 36 years of spot temperature measurements. These measurements were taken by a field technician with a thermometer on their routine site visits when they were measuring manual discharge or water quality. And the goal was to take these measurements weekly, but as you can imagine, over like almost 4 decades, that's bound to vary. So sometimes they didn't get out there weekly due to things like equipment, low flows, funding, etc. And then there were times during snowmelt periods where they were able to visit daily. So all in all, the mean number of measurements per year was around 59 for the lake-fed streams and 33 for the groundwater-fed streams. And another thing to note, just for context, is these groundwater-fed streams are quite small. One of them is shown in this image here, and they often dried up during the summer, which plays a role in having a smaller sample size there. So as you can imagine, there's some benefits and challenges with spot measurements. They're often set aside in favor of continuous data. For the main reason is that you have dial variability. So it's hard to capture the actual temperature fluctuations at a site if you're only getting there once a day or even once a week, like in this case. So that's one of our sort of things that we're starting out with in mind. But we see 2 benefits of these spot measurements. For one, they provide this long-term record that can go back decades. And also they provide you with a broader spatial distribution of data if you want. So you're not tied to budget constraints or whether you can get power to a continuous logger station. The main challenge, like I said, is the dial variability. You need to make sure you're controlling for time of measurement and not looking at artificial biases or trends in your data if you're consistently measuring later in the day or something like that. So you need to control for that. And so for this work at Turkey Lakes, we've addressed these in a couple ways. First, we had site visit times for 22 years of the total data record. So we were able to see that the measurements did not consistently occur later in the day. They were at a standard time generally. And through conversations with our field techs, that held true as well. They almost always visited the sites in the same order. And then also we had an overlapping 10 years of data where we had continuous temperature measurements as well as spot temperature measurements. And that's what you're looking at here. So we have the seasonal mean for each year in each site where we had overlapping data. And you can see that across these panels, for the most part, the two follow each other quite well in terms of trends. Your eyes might go to something like 6 and 7 here, where there's a bigger discrepancy in those absolute values. And we think because this is the winter, there's just more importance on where exactly you are in the stream and where you're taking those measurements. But this is definitely something we kept in mind and sort of had this in mind going forward. Okay, before we dive into the stream temperature data, we wanted to give you an overview of the climate variability. So what you're looking at here is the seasonal mean air temperature minus the long-term seasonal mean air temperature, for example, on the left for each year. And then on the right, it's the same, the precipitation deviation from that long-term mean. And we also take a seasonal scale approach for the remainder of this talk. So we're looking at the winter, which is December, January, February, spring, March, April, May, summer, June, July, August, and fall, September, October, November. So the main thing to take away from this slide is just that climate variability differs between the seasons. So for example, a season like the spring, these annual means are really just bouncing around that long-term mean, and there doesn't seem to be a trend. But in the fall, you see this slight increasing slope here with this linear regression. So that's suggesting that air temperatures in the fall are perhaps warming. And then in terms of precipitation, the slopes were generally pretty flat, except maybe in the spring we saw perhaps some decline in precipitation. But that's just sort of to give you an overview going into the water temperature data. So I know there's a lot to look at in this slide, and you don't really have to take it all in, but if we look at the first 5 plots here are the groundwater fed streams, the right are lake fed, and these are our seasonal means for each year for each site. So the thing I want you to take away from this figure is that there's some variability. Sometimes in some of these panels, the slopes are decreasing and sometimes they're increasing. So for example, in the winter here in these groundwater fed sites, we see these decreasing slope lines. These are just regular like linear regressions for the point of helping your eye see the trend. And then in the spring, there's some increasing here. And then if we look at the fall, we see an increasing trend in the lake fed sites and pretty flat slopes here in the groundwater fed site. And in order to sort of quantify and summarize what we're looking at in this figure, we calculated the nonlinear sun slope for these seasonal means. So each point on this figure represents one of the panels you saw in the last one. And the x-axis is the sun slope, which is our measure of change in temperature per decade. Note that that's per decade. And then the y-axis is the catchment. Our red points represent our lake-fed sites, and the blue represent the groundwater. And the black here is a measure of our air temperature trend. So if we look at winter and summer, these points are really hanging out around the 0 line. There's not much change in temperature going on over our study period, except for 2 of our groundwater fed sites here, 46 and 32, had a small significant cooling trend. And then if we look at the spring, the lake fed sites, no real change here, but the groundwater fed sites had a small significant warming trend between 0.2 and 0.5 degrees per decade. And then if we look at the fall, it kind of swaps. So the lake-fed streams have this increasing or warming trend, and the groundwater-fed streams do not have a trend. The air temperature has a warming in the fall and maybe in the winter here, but these are not significant. So that's sort of what we're dealing with here. There's some warming going on, some not, but it depends on the season, and it depends on whether it's groundwater or lake fed, which is interesting. And oh, just to provide a quantity here for the fall lake fed warming, that's between 0.5 and 0.8 degrees per decade, which is 1.5 to 2.4 degrees over our study period if we say about 3 decades. So that's pretty interesting. Okay, so just some takeaways. We're like very much a work in progress here, but there's some fall warming going on in the lake fed streams and some spring warming going on in the groundwater fed streams. And it doesn't appear that there's any warming going on in the summer, which is interesting because often literature will focus on those summer temperatures and when they're trying to identify a climate change impact. So that's something to keep in mind. And then just wrapping up our use of spot temperature measurements, well, we would perhaps concede that they aren't the best if you're looking for a precise quantitative estimate. But if you're trying to get a long-term look at the trends over time at this longer-term scale, and you can control for that time of measurement and confirm that your data collection methods have been consistent, then the spot measurements might provide a really interesting underutilized resource for trying to like help fill that data gap that we identified. And when we're trying to understand things like temperature response to climate change and forest disturbances that are happening on that longer scale. So I'd just like to finish up by thanking the field techs, so Jamie Broad, Mike McCauley, and the rest of the field staff who've collected these data. And then Melanie Taylor from the Water Survey, who gets us the continuous data. And then this work was funded by the CFS Sustainable Forest Management Program and NSERC. So thank you. I'd be happy to take any questions. And I'd also appreciate any feedback because like I said, it's very much a work in progress.
Great, Danielle. Thanks. That was pretty much perfectly on time. That doesn't get any closer than that. I think it was within a second of 12 minutes. So there is one question in the chat from Chris Spence, who you probably know. Great talk, Danielle. Could the warmer fall lake-fed temperatures be tied to longer open water seasons?
Yeah, thank you for that question. I think definitely we do have access to lake data from Environment Canada folks, and I believe the fall ice on date is getting later. So I think that's probably part of it. Also, we do have the lake temperature data and they are warming a similar amount. So that's kind of helping with the story. But yeah, that'll all be part of if when we publish this, it'll be something we talk about for sure.
The one temperature graph that you show, or the temperature change graph with the red and blue dots, it said it was ordered by catchment area. That was within each class though as well. It wasn't like all of the lower ones were all larger.
Yeah, so it was ordered by catchment area, and the groundwater fed ones are just a lot smaller than the lake fed ones. Which
so do you think that impact, like, did you think the size then is like a confounding variable and it's not just water versus?
I think it's possible. Yeah, it's
okay.
An interesting question. One of our lake fed sites is closer in size, but it's definitely a confounding thing we have to think about. So I appreciate that question.
Yeah, no, it's always hard. Okay, if I don't see any other questions, then I think we have a 10-minute break and we'll be back with Ines at whatever hour you are now, 50, so about 12 minutes. Just a reminder, the CGOHS AGM is Friday evening. There was an email invite that went out. If you didn't get it, let me know and we can get you on the list. There's a young hydrologist session tomorrow at lunch again, and then the WOO lecture is Friday morning. So we'll see you back in about 10 minutes or so. Ines, are you there? Oh, perfect.
Yes, I'm here.
Okay. You want to start sharing your screen and then we'll get started in about 30 seconds?
Yes, of course. 1 second, please. Share screen. Mhm. Can you see now the full presentation?
Yeah, now it's the full presentation. Great.
Okay. So shall I start?
Yeah, so our next speaker is Ina Sanchez Rodriguez, talking about snow melt water partitioning in seasonally frozen soils, insights from field observations. Take it away.
Okay, thank you. Hello, everyone. Thank you for your time today. My name is Ina Sanchez Rodriguez. I'm a PhD student at the University of Saskatchewan, and I work with Andrew Ireson. Andrew and I have had a question that finally is the research question of my thesis, and it's where the water goes once the snow melts. Today, I will share with you our findings based on an extensive observation campaign in Saint Denis research area. So what are the key messages? First, macroreports. We suspect that rapid infiltration and percolation in frozen soils is given by micropores, even in frozen conditions. Infiltrated water coming from the snowpack can reach the groundwater table. Secondly, we found that the groundwater recharge during the snow melt period occurs from two distinctive mechanisms. Firstly, snow melt infiltration, and secondly, thawing coming from the soil moisture. Thirdly, this is important. In literature, it's common to read that the freezing depth of the soil is controlled by the snowpack. What we found is that besides the snowpack, other elements controls the frozen depth, like air temperature, liquid water content, and water table. Fourth, if the water table is shallow enough, it might supply water to the frozen soil via something that we call cryosuction, a process that we call cryosuction. And finally, the midwinter warm events that has been broadly mentioned in this conference so far may cause depletion of the snowpack. And such a melted water that finally can infiltrate the soil may refreeze, but also may percolate down through the macropores until it reaches the groundwater table. In this diagram, we can observe the water balance in the vertical, in vertical for a frozen soil column. Changes in the storage, represented by S, are a function of the liquid and ice content. Melted water from the snowpack and precipitation in soil is split into infiltration and runoff. And finally, the down percolation of liquid water can be drained until it reaches the groundwater table. So what happened? Measuring the infiltration rate in frozen soils is challenging. And the usual methods that we apply for frozen conditions doesn't apply in frozen conditions. So researchers have opted to measure soil moisture storage and incoming snowmelt, along with another type of measurements like groundwater table responses and changes in the soil moisture in depth in different layers, with the objective to catch or to track how infiltration occurs. 30 minutes from the University of Saskatchewan is located the Saint Denis Research Area. Saint Denis Research Area comes on a wildlife management plan and has been used by multiple researchers as an in situ laboratory for hydrological analysis. Around 7 to 8 years ago, two students, a master student from Andrew and postdoc working with Andrew too, they installed over there 2 trances for measurement to make measurements of soil variables in depth. They are Uri and Rosa. Uri's transit, or also we call Lowland transit, is located between pond 107 and pond 108A, and it comes with 8 piezometers, 3 profiles in depth for measurements of soil moisture, moisture potential, and liquid water content. In the north side, Rosa's transit, or upland transit, has 4 piezometers and 1 profile. Okay, results. In this plot, we try to summarize the results. In the top, we have the snowpack and the cumulative liquid rainfall after the winter in green. And below, we have information for frozen depth in dark blue, water table in light blue, and changes in the storage in red. for both Uris and Rosa's transit. The most intuitive observation is how once the freezing process starts, the water table depletes in a process that we call cryosuction. In this process, water migrates from the saturated zone towards the frozen zone due to changes in the matter potential. This is more evident, as you can see, in Uris transit than in Rosa's transit. And that occurs because the water table is shallow or shallowest in Uris transit. The second observation includes the rapid increase of the water table once the snowpack melts. And we can see in 2015, for instance, even if the soil is still frozen. So I propose to you guys to see this in detail. I want to take, for instance, what happened in winter of 2017, 2018. As soon the soil temperature decreases below 0 Celsius and the frozen process starts, the water table depletes. In midwinter event that we had during that winter, which it was caused an depletion of the snowpack, we had also an increment in the groundwater table. And we suspect that that increment is due by infiltration and also percolation of the water coming from the snowpack through micropores. And at the end of the winter, once the snowpack totally melted and the soil was still frozen, the water table had two increment peaks, one from infiltrated water coming from the snowpack, and another from the thawed ice from the frozen soil. This behavior was also observed in Rosa's transit, with the difference that the water table is deeper in Rosa's transit. In this plot, we have the snowpack in the top and the frozen depth in the bottom for both Rosa's and Uris transit. According to the literature, as bigger is the snowpack, bigger is the insulation, and less deep is the frozen depth. However, if we put attention to what happened on 2015 orange line, actually the smaller snowpack has the shallowest frozen depth. And if we check the bigger snowpack, we may find that the deeper frozen depth. So it is clear that the snowpack is not the only factor that impacts the frozen depth. So what we found is that the cumulative days with temperatures below 0 can also influence the frozen depth. As you see here, the orange line represents a warmer winter in which the frozen depth was the shallowest one. However, the water content before freezing starts also influences the frozen depth. Let's see these plots. Again, we have in the top the frozen depth, and in the bottom the Uris and Rosa. I'm sorry, in the bottom the liquid water content for both Uris and Rosa's transit. As we can see, as a higher is the liquid water content in the top layers before freezing or before the freezing process starts, less deeper is the frozen depth. And that is clear in the orange line, but also in the red lines when we have the less water content in the top layers. So what are our take-home messages? Firstly, micropores. They play an important role, especially how the groundwater recharge during the snowmelt. Secondly, groundwater recharge occurs by two mechanisms. Firstly, by the snowmelt water infiltration, but also by thawing of the soil ice. Thirdly, not only the snowpack is important. For taking into account how deep is the frozen conditions in the soil, it might be important to see the air temperature, the liquid water content, and the groundwater table depth. We find that if water table is shallow enough, then by cryosuction, water can migrate towards the frozen zone. And finally, and really important for people putting an eye in climate variability and climate change. During those midwinter events, warm midwinter events, the groundwater table can be recharged by water that infiltrates the soil due to snow melt in those small periods. Thank you.
All right, so we have, I think, almost 5 full minutes for questions. Thanks for that chat. Really interesting stuff. I just love that sort of like pure physical hydrology stuff. So do we have any questions for Crinus? Anybody out there? Nope, doesn't look like it. So we will wait. Oh,
can
sorry,
I ask
there we
a
go.
question?
David?
Yeah. So you're talking about the importance of macropores in water infiltrating down. And I'm wondering if you have any ideas on how those macropores are formed. What are we talking about? Are we talking about maybe desiccation, fractures, old roots, burrows, or are we talking about large porosity that remains gas filled? Can you speak to that? Have you thought about that at all? I understand maybe that's beyond the scope of what you've done so far.
Well, thank you, David. Yes, I mean, I had been making this question in my mind because it seems that, usually as a physics and we try to reduce the system, but seems that the micropores that they comes from actually biological processes that includes the bioma living in the ground, but also management process for agriculture may impact how the infiltration occurs. So macropores basically they are considered like after larger porosity, these pores that are created by this kind of processes. And it seems that they are very strategic to understand how the infiltration occurs and the groundwater table recharge.
Yeah, very good. Thank you very much. I think that would be a really interesting thing to explore next, and that might have some interesting applications on understanding infiltration processes. So very good. Thank you. Thanks
to you, David.
Thanks for the question, David. Do we have any other questions? We've got a couple of minutes before our next speaker.
Yes, this is Spiros Beltaos. Could you please elaborate a little bit on the process of cryosuction?
Yes. Let's think that we have a soil column that is unsaturated. And we have a frozen front coming from the top to the bottom, which is basically reduction of the temperatures in the different depth layers. What happened is like changes in the phase from liquid to ice near to the soil particles increases the matrix potential, which is basically the suction. So what we found and what is available in the literature, it's like water migrates from the saturated zone towards the frozen front because this incremental suction, which is basically a consequence of the ice in the frozen zone.
Thank you very much.
Thanks to you, Aspers.
Any other questions? We only have a minute now or so. Okay, well, thanks very much. We'll get our next speaker set up. Pamela, if you're there, if you could start sharing your screen. Excellent, thank you. And then I'll introduce you in about a minute, and then we'll get started. Just a reminder of the AGM Friday afternoon, evening, depending on where you are. The WU lecture Friday morning, and the young hydrologists have another workshop meeting session tomorrow. I believe it's at lunch again. And so those are all, I think, really interesting things to check out to make sure that you're in the loop with what's going on. And then hopefully this will be the last online meeting we have for a little while. We'll be in Banff next year, which will hopefully be wonderful, and everybody will get to see everybody again.
Okay, are we ready?
Yeah, I'll introduce you, and then the clock will tick over to 5 after, and then we'll be good to go. So our next speaker is Pamela Tetford, talking to us about assessing channel geometry in response to land use disturbance in a low relief glacially conditioned region.
Thank you very much. My name is Pam Tetford. I'm a PhD candidate at the University of Toronto. And our research is considering the impact of land use disturbance, in this case, urbanization and tilled agriculture, in the examination of a channel's hydrogeomorphic response. So to explain a little bit about the geomorphic response, the volume of water that is channeled by a river determines the river's hydrogeomorphic response, and it actually shapes the channel in which the water is traveling. And research suggests that a bank full flow, which is the highest level of water that the channel itself can carry before overflowing onto its banks, this flow level will generate the most effective shear stress on a channel's boundary in terms of the frequency and magnitude that these events are happening, and that this will most influence the channel's form itself. And we have two approaches to identifying this channel forming flow. One is based on historical gauge data that is collected to determine the flow frequency that these floods are occurring, and another is based on a channel's form or its geometry, the shape of the channel itself, and then we can calculate this bank full flow with the continuity equation, where we take the width times the depth times the velocity of the flow itself. And more recently, however, though, land use is being shown that it's modifying this flow of water across the landscape to a channel, and this is impacting a channel's natural hydrogeomorphic response. So in light of this, our study is looking at three objectives. One is to develop a downstream hydraulic relationship using historical hydrological data in order to estimate a characteristic bank full flood discharge. In this case, the Q2 flood, the 2-year flood interval. This is considered to be representative of an accepted representative of bank full flow, this 2-year recurrence. Then secondly, we want to derive bank full flow estimates based on surveyed channels. And this takes into account channels that are actually physically surveyed in the field, and then boundary conditions that are extracted through GIS files to incorporate all of the morphological criteria that's necessary. And then the third objective is to compare bank full flow estimates based on these gauge data relationships to what is actually being seen in the field with the channels surveyed. And at the same time, considering how the influence of upstream land use is impacting it. So our study uses field observations, digital GIS files, and then we use some accepted empirical relationships as well. So our study takes place in Southern Ontario, which accommodates approximately 35% of Canada's rapidly increasing population. But the urbanization is in a clustered format. It's not right across the region. We have a low relief in comparison to out west or in Quebec. And it's a glacially conditioned region, which impacts the superficial geology. Our glacial history has left a thick deposit of sediments that have encouraged some fertile soils in many areas. So these soils support Ontario's agricultural development. For our study, we used 207 gauge stations around Southern Ontario that have been operating for at least 10 years of continuous data. We have 140 surveyed sites in river reaches that provide us channel width measurements, depth, and then the median grain size, the D50, which is important for determining the friction within the channel itself. And then boundary conditions are extracted in a GIS environment that provides the gradient of the channel and the surrounding land use, the upstream land use more specifically. The lower image here illustrates the clustered urbanization in the gray for Ontario and the extensive agriculture that takes place in this area. So we use two types of gauge data. We have the annual maxima series, the AMS, and the partial duration series, the PDS. Both of these data sets are derived from the mean daily flow. And each of these data sets for each of the 207 gauge stations were fit to 4 different statistical distribution models: the log normal, Gumbel, log Pearson type 3, and the generalized extreme value distribution, using Monte Carlo simulations and 4 different goodness of fit criteria. And this is to get the best fit in order to be able to model this Q2 flow. Typically, the 2 graphs that you see, the top one being the AMS data set and the bottom, the PDS, we found that the PDS provided a better fit for these high frequency but low magnitude floods that are relevant to this Q2 bank full flow, because we're looking at the more frequent flows, not the 100-year floods that you would get. And in general, what was interesting, the AMS data sets, we found that they did not similarly point to one specific statistical distribution that should be used, but they were spread out across the log normal, Gumbel, and LP3 models. But the generalized extreme value models just were the best fit in a limited number of cases. However, the PDS data sets, the partial duration series, we found that they overwhelmingly suggest that for Southern Ontario, for modeling flood frequency, a log Pearson type 3 model should be used. So looking at our models then, we used a cumulative probability approach to estimate this 2-year flood recurrence for each gauge station. And then it has been plotted against the cumulative drainage area for each of the gauge stations to develop a discharge drainage area relationship. The equation there shows that the equation that we are striving for, it's an accepted power law relationship between drainage area and discharge, where the coefficient alpha and the exponent beta is empirically derived using statistical regression. And this allows us to take the information from the gauge data and apply it to each of the ungauged survey sites that we have throughout Southern Ontario. On the plot that we have here, it has both the AMS and the PDS data sets. And then also the black line represents other research findings. So our results were very similar, but what was interesting was, even though the PDS data sets had produced a better fit with regard to the high frequency, lower magnitude floods, once they were logarithmically transformed in order to create this accepted power law relationship, they generally produce the same results. So either the AMS or the PDS data set is appropriate if you are going to be using logarithmic transformation. So now to compute our channel form bank full based on the physical shape of the channel, we had the width measurements from surveyed data and the depth. And then the velocity, we used an empirically derived Lacey equation, which has previously been shown to effectively estimate the velocity of the flow based on the boundary conditions. And so the plot that you see there is using the same discharge drainage area relationship, only in this case it's using the what we refer to as the geometrically derived bank full discharge. And so it's replacing the hydrologic one that was done. And you can see with the Loess curve there has the 95% confidence intervals, and it's showing that it's a non-linear pattern that we have when we used the actual channel form as an estimate for bank full. And the original hydrometric relationship is the black line there, so you can see it in comparison to the other one. In the smaller drainage areas, less than 100 square kilometers, there's a much higher estimate of bank full discharge when using the actual channel form as your estimate for the flow that's being carried by the channel. So this suggests that the estimates that are being captured by gauge data are being underrepresented in, it's an underrepresentation of the flow in these smaller drainage areas. So when we factored in land use then, we looked at the width to depth ratios. A channel's width to depth ratio is often considered as a scaling relation when you're looking at a channel's cross-sectional form, because it quantifies the relative erodibility of channel banks versus the channel beds. The graph on the left shows the width to depth versus the level of disturbance. So we're looking at urbanization and tilled agriculture combined in Southern Ontario as your key disturbance types. A two-key comparison of means indicated that there's a statistical difference between the width to depth ratio of the highly disturbed river reaches compared to the moderate and low disturbance reaches. The image on the right is the same one that you saw on the previous slide. However, this time we have categorized the points for the survey sites based on their level of disturbance. And for comparison, again, the hydrometrically derived drainage area discharge relationship is indicated by the black line. So we see that in the smaller catchment areas, less than 100 square kilometers, that these river reaches are being impacted by proportionately high levels of human disturbance. And in some reaches, this is also occurring with the moderate levels of disturbance, where they are plotting again above this hydrometric relationship. So this again is suggesting that the channel form may be enlarged, possibly by these flashy instantaneous flows that aren't being captured by the mean daily discharge. So we've concluded from this then that when modeling AMS and PDS data sets, the PDS one does suggest that a log Pearson type 3 model is appropriate, whereas the other ones you need to do an individual goodness of fit criteria. And these high frequency, low magnitude floods are better using the PDS data set unless you use if you're logarithmically transforming them, then you can use either one. The smaller drainage areas then are creating bankful discharge estimates from these smaller drainage areas are larger if you're actually looking at the channel form. And that this is happening particularly where there's moderate to high levels of land use disturbance present, which is interesting because Southern Ontario as a whole, agriculture creates a lot of the disturbance, and generally we think of high disturbance being caused by urbanization, whereas Ontario's urbanization is clustered and not impacting a large area. And river reaches that are impacted by high land use disturbance have a significantly lower width to depth ratio. And the takeaway is that when modeling channel response to changing hydrology, the spatial patterns of land use change should be considered.
Okay, thanks very much, Pam. That's our time there. If I could get you to stop sharing your screen, and we'll get our last speaker of the session up and running. That'll be Angela, talking about understanding snow representation in the NOAA MP model through a single column experiment. So is Angela there? I saw her earlier. I thought I saw her earlier. Are you there, Andrew? Or Angela with the CMOS 3 CGU?
I don't think
Okay,
I've seen her.
Okay, well, if anybody has any questions for Pam, then we can ask them. I thought it was really interesting, Pam. I was thinking at the very beginning of your talk about just with the channel geometry and, you know, Manning's equation. Would you say that Manning's is just a much more simplified, quick and dirty version of what you're doing, or totally unrelated? I don't really know this area of research, so forgive me if my question is quite ignorant.
The Manning's equation was one of the ones that I explored. Actually, Lacey and the Cooligan equation were the two that were used to compare to see if I was getting roughly the same velocity. However, but because they were the ones that were most used in other research, but the Manning's one was one that I also explored as well. That's where the D50 came into to play.
Okay. Okay, I'll just check the chat quickly to see if a question is in there. Nope. So I don't see our other speaker, and so I'm going to assume that they're not here. They got the time zone wrong. I'm not sure. Maybe they're having technical issues, but I'll hang out for another minute or two. But if people need to go or want to go, then that's fine. We have the General Hydrology Part 3 coming up this afternoon, which I believe Barrett will be chairing that session. Is that right, Barrett?
Yeah, that's right.
Yeah, perfect. Okay. Okay, well, we'll see everybody in a few minutes. I might pop in for a talk or two, Barrett, if you're still there, but mostly I won't be.
Okay, sounds good.
Okay.